great. Thanks for inviting me, Oren. We've known each other for some time. And I think, so as he said, I'm a cognitive scientist. I also work at MIT and CSAIL, the AI lab there. And I really have a foot in each of these communities. I guess if I had to choose, I would choose to call myself a cognitive scientist. But I've always taken a reverse engineering approach. And that's what I've tried to give here in the title. I'm trying to really do two kinds of things here. I'm trying to figure out how to describe human intelligence in the same kinds of terms you would use to engineer an AI system, in particular a human-like one. I try to avoid using the word human level because that sets, people like to talk about human-level AI, or really they don't like to talk about it, but that I think sets a sort of weird set of standards which are debatable. But human-like, I think we're all interested in trying to make AI more intelligent in human-like and more human-like ways. So that's a project I work on. I think it's directly connected to trying to have a better computational understanding of how the human mind works. And I hope we can have a discussion about how we can maybe work together on that in some way. Okay, so I'm gonna give this talk. It's very much based on a talk I gave a few months ago at a AAAI Spring Symposium, where at least a couple people from your institute were. But anybody saw that talk by any chance? It's kind of good if you didn't, because I'm just checking that most people haven't seen it. Okay, good, nobody's seen it. All right. So that was a meeting of people interested in knowledge representation and reasoning in some form, and trying to take a mix of probabilistic approaches, symbolic approaches, neural approaches. You mentioned, I am kind of, I guess, associated with probabilistic approaches, but like in your work, like what I think is a lot of the best work being done here, it's the right answers, I think, are not simply labeled by those terms, right? I will talk about a certain approach, technical approach that some of my colleagues have been working on, that we've been working on, what we call probabilistic programs. And this is, I think, just one example of an approach that tries to combine the best of probability for what probability is good at, structured logic-like representations for what that's good at. So at this meeting, there was a great meeting. There luminaries, truly distinguished people. Jeff Hinton, Doug Lennett were both there in the same session. I don't know, all sorts of people. And what was interesting looking at what everybody was talking about there, and I think, to some extent this is hopefully you'll see this as a fair characterization of what a lot of the work is here. At least, I was trying to get a sense of what you guys are doing from the website last night, and there's a lot of cool projects going on. But, the things that have gotten the most attention, I think kind of fall into the category of things I'm going to criticize here, or just say, here, add in a complementary approach, which is there's a lot of emphasis on how we could capture common sense knowledge and reasoning in terms that are sort of very much oriented around language, either because we're going to do machine reading, or because we're looking to language as the sort of the main target of common sense. But what I want to emphasize, and this is my perspective coming as a cognitive scientist, is something that's missing from that, which is a sense of the world and our intuitions, our common sense intuitions about the world, that in actual human minds come to be much earlier and much more fundamental than language. I'm going to talk a lot about developmental psychology, the study of really young children, even infants. One of the things I can hope to do here is just give a little bit of a tutorial introduction to some topics that probably most of you don't know about, but which I think are really quite inspiring for AI. So there's this sense in which even a 12-month-old baby has more common sense than any of the AI systems that we've built, right? And this is 12-month-olds don't really have language. They might know a few words. They might be able to say a few words. But there's what I would call sort of a core knowledge representation reasoning capacity that's in there, that's develops through some combination of genetic programs and experience. Maybe a reasonable sort of analogy is like learning to walk, right? I don't want to get into big debates of nature versus nurture or whatever, but I think it's pretty clear and uncontroversial that pretty much every normal human child learns to walk. Of course, you have to have other people around walking. It's part of how we learn is by seeing other people do this awesome thing and thinking, wow, I wish I could do that, right? But clearly there's some combination of the ways our bodies and our brains are set up genetically and the experience we get that leads any normal human child to walk by about this age. And there's similar developmental timelines in cognition. And I think if we understand those can be the real building blocks towards not just a more sort of linguistic, later developing common sense, but really, I think the true scaling route we want. I mean, everybody who's trying to work on human-like AI or human-level AI needs some scaling path. We all know that. You need to start with a more tractable version of the problem and then scale it up. And people debate, maybe this is just another way to frame the big issue that we're talking about. People debate what's the right scaling route. I think if you look to the science of human learning, we only have one example of a successful scaling route. Just like we only have one example of human-like intelligence, namely humans, we have exactly one example of a scaling route, which is the way that human children learn. And there's a long tradition of AI people saying, oh, we're going to build an AI system that learns the way human children do, right? You know, whether it's Turing in his first paper on the Turing test suggested that. Minsky often suggested that. John McCarthy suggested that. Some of the things that you guys write suggest that, like a focus on school, you know, what you can get out of fourth grade biology text or something. You know, it sort of has that flavor, right? But I think, you know, with all due respect to the brilliant people who've said this, none of them pretty much know what they're talking about. Maybe a few people here do, but for the most part, the idea that you're going to build a machine that learns the way a human child does is mostly based on somebody's intuitions about how children learn, rather than the serious science that's emerged over the last couple of decades of studying how children learn that almost nobody in AI knows about. So if I can do anything here, it's hopefully to convey that there's a really deep, interesting field that is not so accessible to outsiders from an engineering background, but with the right approach, and this is sort of the longer-term project I'm trying to work on, can become accessible to you. Now, I had a few slides which I think, for reasons of time, I'll probably mostly skip through unless people are particularly interested in kinship. At this workshop, a lot of people gave examples of kinship. Do people know this sort of famous example of, this is like an example that Jeff Hinton introduced, and Doug Lennett was working on it, and half of the other people there, you know, were working on it. It's sort of a, so I mean, I guess I can go through it very quickly just to motivate what I think is really true common sense, although I'm going to be talking about adult stuff before I move to kids. So, you know, the idea that we might try to learn the kinship structure in English with some combination of, you know, first order logic and maybe some statistical learning, to cite some other cool stuff across the body of water, like Pedro Domingos's Markov logic. You know, there's lots of combinations of probability and first order or higher order logic that do smart things in knowledge representation, that might allow you to do this kind of reasoning that, you know, learn things like if X is Y's brother and Y is Z's parent, then X is Z's uncle. But, you know, if you think about from a kind of a common sense point of view, our knowledge of kinship reasoning, just to take one example, goes way beyond what you can get from just the kinds of, you know, these natural logic expressions, things that look like linguistic expressions of basically first order logic. We can take a new person and reason in ways that you know, again, tap into our intuitions about actual people and families. So here's a few questions to just seed your thinking here. So we have a new person, Boris. Is the mother of Boris's father his grandmother? Yes or no? There'll be a lot of interactive demos in this talk, so you should answer. It'll be more fun. Yes, okay. Is the daughter of Boris's sister his grandmother? No. Is the mother of Boris's sister his mother? Okay, yeah. I don't know. Is the son of, good question, right? Is the son of Boris's sister his son? No. What did you say? No. Someone said like, hopefully not. Yeah, right, hopefully, right. Okay, well, let's spell out this world. It's not Game of Thrones world, but it might be some other TV show. Suppose that Boris and his family were stranded on a desert island when he was a young boy. How does that change your belief in this statement? Might raise it, right? Okay. Yeah, maybe? Okay. Depends on how many other people were stranded there. Suppose they were stranded alone, or with one other family, or two other families, or 5 other families, or 50 other families. Again, here's a little bit of probabilistic reasoning, right? Where you can imagine, well, if they were stranded there alone, okay, maybe, you know, things happen. But, you know, if there are 50 other families, they might as well have been in Seattle. Okay. And then suppose we tell you, well, they were rescued when he was 12 years old, 15 years old, 20, 30, 45 years old. All of these facts that fill out the story are going to change how you think about this based on things you understand about physical proximity, space and time, course of human events, and so on, right? Take another example. Is the son of Boris's wife's son his son? Here we probably would say, hopefully, yes. I mean, unless there's some remarriages, but let's say they've each only been married once. Okay, fine. But now we can tell you more things like this. Suppose I tell you that Boris is an international businessman who often takes long trips away from home. Okay, that might change your probability. But but he gets very jealous, and so he locks his wife in the basement during his trips. Oh, okay. So all that laughter tells you understand how this is going to change things, right? Unbeknownst to him, his wife used to be a professional escape artist. Okay, so it keeps moving, right? And again, in AI, we might have, at some point, we might have, and maybe still call this non-monotonic reasoning, right? But it's not just a problem for traditional logical reasoning that your degrees of belief go up and down as I tell you more things, and it's not just enough to invoke probability, right? I do want you to get a sense of how the degrees of belief push up and down here, but it's about understanding the actual world that we live in, and I just don't think that sort of trying to learn a bunch of logical formulas in language and even with probabilities is going to solve the problem. So this is that was a bit of a tangent, but it helps to show that I think hopefully the connection. I'm going to mostly talk about a much more sort of immediate, core, infant, child-style common sense knowledge. But I think if we want to solve problems like that, or just understanding stories, basically, you're going to need a common sense understanding, which is definitely grounded in language, but grounds ultimately on meaning and understanding in the kind of things I'm going to talk about here, which is basically immediate stuff in the world. So I'll talk about this common sense core and a little bit about learning mechanisms. As Oren said, I've studied learning. It's a lot of what I'm interested in. But I think if you really want to tackle common sense, learning is hard. And you first want to understand the knowledge that you're trying to learn so that you learn the right things. Depending on how time goes at the end, I have a few slides on learning, so we can talk about that. I think maybe what I want to try to do is cue a discussion with anybody who wants to talk with us about it today or as long as we go, about how learning could work. If these are the right targets of learning, then we can talk about how do you solve the hard problem of learning it. And like I said, there'll be, this isn't a super technical talk, but I will also try to introduce some technical ideas from what we call probabilistic programs. This is sort of also, again, in the talk I gave at this other workshop, it was kind of part of a twin billing with Noah Goodman. Just curious, how many people know Noah Goodman and the church probabilistic programming language? Anybody heard of that? Okay. So Noah was a postdoc a few years ago in our group at MIT. Now he's a professor at Stanford, together with a few others like Vikash Mansinga, who's a research scientist at MIT now. They invented a particular kind of probabilistic programming language, which I think has a nice. I don't suggest that you use it for most of what you're doing, but I think it has a nice set of conceptual foundations which illustrate something about the kind of approach we're talking about. So I'll say a little bit about that as we go on. Okay, so what is this common sense core that I keep talking about? Well, it's this idea that from very early on, in some form, almost as early as you can look, which involves experiments with, say, 2- and 3-month-old infants. I'll show you some examples of those in a second. Humans structure their thinking, their understanding of the world, in terms of a basic set of concepts of what you could call intuitive physics and intuitive psychology, right? An understanding of the world in terms of objects that are physical things, not just sensory, but physical, that live in 3 dimensions and that are subject to things like forces and have properties like masses. So it's a kind of intuitive classical mechanics in some form. And also an intuitive psychology, so an understanding of agents who don't just move through the world, but plan their actions in goal-directed ways, like agents having beliefs and desires and that sort of thing. And just as the math of physics, classical physics, something like Newtonian mechanics, the math of kind of intuitive psychology is something like classical economics. As I'll try to show a little bit, the math of expected utility, basically probability and utility, it's notoriously problematic for describing a lot of complex human decision makings, but for describing the sort of limited range of decisions and plans that a baby can understand, it's actually very good, and it's a very good way to describe the math of our intuitive theories of mind. So I'm going to try to show you how we can describe mathematically, computationally, this early emerging intuitive physics and psychology, and use that as the basis for building our common sense representations. I think that's mostly what I want to say about this. I guess one other thing I'll say is, again, I'm going to mostly talk about common sense knowledge that exists pre-linguistically, but language certainly builds on this and amplifies and extends it. So as children get older, their intuitive physics and intuitive psychology gets much more powerful, and common sense extends to a lot of other domains. But this is kind of where it starts. This knowledge also is very much of the glue of cognition. So it's sort of in between perception, action, and language. I'll mostly talk about it in the context of perception. funny resolution things happening here. These are examples of what I like to call common sense scene understanding. So I think of the common sense knowledge here as the target of what perception's really about here. And then it's also going to be the stuff that if you're going to act on these scenes, it's the targets of your action, and if you were to describe them in language, the substance of what you're talking about. So you can look at these scenes. The ones on the left are meant to sort of get at this intuitive physics. The ones on the right are meant to get at this kind of more intuitive psychology. And in each of these cases, you can do the standard thing that people in computer vision have been trying to do for a while, have had a lot of success with. There's various data-driven learning techniques that I'm sure everybody here is familiar with, whether it's deep learning or anything else. You know, the classic target of vision is detecting what is where, finding objects and where they are. And you know, most of the time that means these days still putting regions like in images and labeling them. The real stuff of scene understanding, again, something you can see even in young infants, is objects in 3 dimensions, not just regions of pixels in 2 dimensions. But more than that is the physics of the scene or the psychology. So in this scene, you don't just detect a lot of objects, but you understand what's supporting what. So you know that if you were to remove the table, that a bunch of objects would fall. If you were to bump the table, maybe some of them would fall off, not others, depending on how hard you bumped it or where you bumped it. Maybe a certain bump might cause this tire to roll over, not others. There's a bunch of objects kind of in the back there, which you don't just see as hanging in midair, you see them as somehow either attached to the wall or hanging on things that are attached to the wall. And you understand that some of these objects you could just pick up and lift off with relatively little effort. Others you'd have to yank because they're stuck into the wall. Or this scene here, this house, right? You don't have to know anything about building a house to know that not only are there a bunch of pieces of wood in that scene, but there's also a bunch of nails, right? You can't, or some kind of attachments, right? You can't see any of them. They're smaller than individual pixels, but you know there have to be some things attaching some of these pieces of wood to others. Otherwise, the whole thing would fall over. These are just a few of the many kinds of intuitive physical inferences that we do, just kind of without really thinking about it, right? Here's a scene from our local cafe in Cambridge, Massachusetts, where the barista described this as a disaster waiting to happen. Notice this is a dish bin with a bunch of mugs and glasses and plates stacked up in it. And he knew, he was going over to pick it up, and he knew, wait a second, I can't just go and pick this thing up like this, or those dishes are going to fly into the floor and make a big mess. So he knew he had to restack them and maybe take them in two trips. Again, he didn't really have to think about it, but that's the kind of common sense knowledge we're interested in. Or in these scenes over here, you know, we recognize people, we get some sense of maybe their relationship to each other, but we also get a sense of what they're thinking, what they believe, what they want for themselves, what they are thinking and want with respect to other people. There's these mental states that we talk about in intuitive psychology are fascinatingly recursive. So think about, for example, this crossing guard here, right? What's she doing? What's she thinking? What's she thinking about what other people are thinking? So notice she's kind of looking in this direction, holding up that stop sign. She's probably either looking to see if a car is coming. Maybe she seems to be staring in a way that suggests perhaps she may be making eye contact with a driver, trying to see if that driver has seen her, to know that he should stop, because she knows that there's these people back there who may not know about that car. That's certainly they're not looking in that direction. I mean, it's her job to make sure that that guy sees them and stops accordingly. So our ability to look at these scenes and understand what different people believe and desire about other people's beliefs and desires, that is again the sort of heart of this common sense core that you can see in scene understanding problems like this. And I think hopefully it should be pretty clear why for a lot of different AI applications it would be great to be able to harness this sort of knowledge. These ones are more about things like robotics and self-driving cars and so on. But again, I think that whatever your AI goal is, it can build on the same kind of knowledge. And it can build even more fundamentally. You don't have to look at complex scenes like this, like these ones. A lot of what we're going to be looking at are scenes more like what you get when a kid is playing with blocks, or playing with another kid, or playing with other kids, playing with blocks, or learning about things for the first time. So even before you learn 4th grade biology, you learn about how magnets work, or silly putty, or a touchscreen device, that sort of thing. And in a sense, I think this is the more natural scientific target, and even kind of, I would argue, engineering target than just what happens in schools. It might be that school textbooks are more accessible to a lot of researchers, and so it's good to work on them. But I think it's got to go together with studying the earliest forms of discovery that even these young children are making. About objects, I think I'll mostly skip this. This is just a lot of words about just to pick one area of infant knowledge in intuitive physics. The main point of this slide is just that a lot is present before language. So here I've just highlighted in blue or purple some of the very earliest understandings of meanings of words, but there's a lot of really interesting stuff about this visual intuitive physics, and I'll show it more visually. So these are just examples of studies in the literature, and I put a couple of people's names here, like René Bayesian, Liz Spelke. How many people have heard of Bayesian or Spelke? Okay, good. How many people have heard of Piaget? Okay, so Piaget is much more well known as sort of the founding father or grandfather or great godfather or whatever of developmental psychology. And it's good that people know about Piaget. A lot of AI researchers, when they talk about developmental robotics or building machines that learn like children, they often talk about Piaget. Minsky would often cite Piaget. But again, if your knowledge of developmental psychology begins and ends with Piaget, that's kind of like as if your knowledge of AI begins or and ends with Minsky, or kind of worse, or not worse, just older. Great, but older. A lot has happened since. And people like Bayesian and Spelke are some of the main people who've made that stuff happen. Just as the fields of, say, let's take machine learning as an example we all know, has really transformed in the last couple of decades, the same is true for the study of human learning. It's really true that if you go back to, say, 1980, it was hard to say in any sense that we really had an understanding of how infants understand the world or learn. And in the last few decades, we've laid the groundwork for a real science of human cognitive development. So examples of the kind of studies that Bayesian and Spelke and their colleagues have done are shown here. These are all examples of looking time studies, where the way you assess what a kid knows, these are, again, like when you're talking about a 2-month-old infant, you can't ask them a question. They can't even reach for anything, so you can't ask them to do anything. The ability to reach and pick up objects really only kind of comes into play around 6 months. And yet, by doing the right kind of studies, you can show that even these much younger infants already have a sense of the physical world and objects, what Piaget called object permanence, and what he famously argued was an achievement of 12-month-olds. It turns out that well before 12 months, infants have all sorts of much more sophisticated knowledge about objects that go beyond just the fact that they don't wink in and out of existence, but that they have real physical properties. So for example, in this study with just 2-month-olds, infants understand that objects have a sense of kind of solidity, and that objects can't just are unlikely to pass through other solid objects. So you have this wall here, a ball rolls towards this big wall, a screen comes up, and then the ball rolls behind the screen, and the screen is then lowered, and the question is, what does the infant expect to see? So the way you do these studies is you show them something which is either expected or surprising, and you look at how long and maybe where they look in the scene. And just like you, if you see a cool magic trick that surprises you, you sort of look longer or want to see it again. Infants do the same thing. They'll stare longer or kind of want to see it again, and you can then get a sense of what their expectations were, when or whether you defeated those expectations. So in this case, just like you, if the ball rolls behind the screen and then when the screen is removed, the ball appears to have teleported to the other side of this wall, that's surprising to the infant. They look longer than if it just stops right here, the expected event. So that's showing just one example of showing this understanding of kind of rigidity in motion that respects that physical constraint. There's a lot of others which, since time is short, I probably won't really go into. I'll just point to this because here we'll talk a little bit about that when I go to some of the more computational parts of the talk. There's a whole interesting developmental timeline of how infants come to understand support. So how they understand that objects don't just float in midair, suspended there, but like what counts as an object, as a stable supporting relationship. So the stuff I was talking about with the table in that crowded workshop scene before, in some limited form, infants are coming to understand that over the first year of life. Maybe it's also just to kind of get people's intuitions going in the right direction, fun to look at a couple of videos from YouTube. Maybe the one on the bottom is kind of the ultimate YouTube video, because it's got a baby doing something cute with a cat. You can just watch the baby here. So like the one on the top, he's stacking up cups, although here he's doing something fun, which is stacking them up on a cat, seeing what he can do there. maybe he knows that because of the cat surface, he's not going to have much success stacking them up into a tower, so he's content just to put them on there. Until then, one of them goes off. He's like, oh, that's cool. Well, maybe I'll try to reach for it, and that's not going to work. All right, so maybe I'll just put them all over there. And notice he remembers that there's one back there. So talk about object permanence. He has a very sophisticated kind of object permanence already. Anyway, I mean, there's a sense here, yeah. There's a sense here in which the world of objects is real to this kid in a way that it isn't really to any of our robots or any of our AI systems. So I'm not saying you all have to do robotics, but what I am arguing is that if you want to understand cognition, including more sophisticated reasoning and language, I think you want to build on the common sense knowledge of physics that kid already has there.
Just,
yeah.
Can I ask a quick question? So this seems like there's a great analogy here, because we've had the opportunity to talk to brain scientists, and they're very interested in where of knowledge, where in the brain it is. And it seems like what you're alluding to is there's a lot of interesting developments about the when of knowledge.
The when and the what.
Well, so that's where my question is going.
Yeah.
If we factor out the where, because arguably that's less relevant to AI, and we factor out the when, because on a minor scale we don't really care if it happens at 3 months or 6 months, or 12 months, but that might be a huge innovation, relative to Piaget. We very much care about the what and the how. So if you take, for example, something like supports, love to understand.
I'm going to, so I will, yeah, I mean, if you're getting impatient to see a little bit more, I will talk about that. Now, if you read the papers by people like Bayesian, who did a lot of that work, she will describe the what in her terms, and it looks kind of like a decision tree, actually. She gives sort of decision tree of rules. I think it's sort of an implausible, I mean, it's an intuitive way to organize her findings, but I don't think it has nearly enough power to capture our common sense physics. It's more just a way to compactly describe her findings. So I will talk about, and this is the contribution that we've tried to make in our work, is how could you describe the what in powerful enough engineering terms that you can use for a wide range of reasoning tasks. I will talk about that. But I also want to make a case that when is important and even where is important. I actually had some slides which I probably cut out so some of my colleagues, looking partly at the work we did on this kind of modeling of intuitive physics, actually went to see, is there some part of the brain that seems to do this? And I think there is a lesson to be learned. If there's a part of the brain, a very consistent part of the brain, a big part of the brain, that does something consistently, it is one piece of evidence that it's somehow core in our common sense. It turns out a lot to be, in some ways a lot easier maybe to figure out the intuitive physics part of the brain than to figure out whether there's even a distinctively language area of the brain. Again, something, not to knock too much on language, but kind of. Also, when is important. I mean, if a certain piece of knowledge is present before another piece of knowledge, it is partly a sign that maybe that later piece of knowledge might build on this, or that if we want to try, just try following the scaling route that humans do, then it's telling us something about how we're going to have to do that, right? And I think it's very telling that while there's been a lot of progress in different corners of AI recently, whether it's in machine vision and deep learning or robotics or language understanding, it often looks mistargeted or chronologically mixed up from a developmental point of view, because people are focusing on maybe the things from a technological point of view. I mean, it makes a lot of sense for Google to do this, right? Or Microsoft or whoever, to focus on the things that we as adults most want our machines to do. But if you're taking the longer term view, which we do and you guys do, I think, then it might be worth reconsidering which tasks are most fundamental, and when is really important to that. On the learning side, also, again, this is stuff which I think is hard. We've tried to model this.
Just one last point about that. I think there's a distinction between the ordinal nature, what comes before what,
and the time. Good point.
So
good point. Good point. And the exact timing is also, I forgot to say this, something you should take with a big grain of salt. Right. So these numbers, hard to know whether what those really mean. Yeah, so it's really more the ordinal relations that I'm trying to emphasize. Exactly. And even those are big error bars on that. But there's some stuff we know, and I'm trying to convey what we know with the appropriate amount of uncertainty. There's another issue is really how we learn. And I think there's really sort of two great insights of the last couple of decades of developmental psychology. One is this early common sense core intuitive physics and intuitive psychology, and the other is something about the learning mechanisms, which you could describe as sometimes called the idea as the child as scientist or something like that. it's probably the person who's written about this in the best way, in a popular way that you might know, is Alison Gopnik. Anybody read any of her books? Gopnik, or Alison Gopnik? Okay. Well, you could read. She's written a book called something like "The Scientist in the Crib." Maybe another one called "The Philosophical Baby." Is that by her? Maybe that's by someone else. I know there's a lot of books that are basically like babies and children are a lot smarter than you think, kind of like scientists. Another way that you might contrast this view or talk about this view of learning, to contrast it with the sort of current trends in machine learning, is this idea that, again, you know, if our common sense knowledge is something like these intuitive theories of physics analogous to some kind of Newtonian mechanics or intuitive psychology, then learning has to be some kind of theory building. It has to be something more like what scientists do. And you could contrast this child as scientist view with what you could call the child as data analyst, right? Like if something like deep learning or just what most conventional statistical machine learning looks like, if that were really the way to describe how children learn, you know, that would be like saying that the way to do science is just big data analysis. Now, again, big data is really cool and useful, and there's a lot of things that maybe, you know, insights that might reveal to us. But in some sense, the way when children are learning about the world, they're more like in the setting of Galileo, like dropping things and seeing what happens. And the kind of more classical idea of science, of having relatively simple theories, seeing what they can explain, doing experiments to test between them, and getting into a sort of a loop of theory building, looking for coherent principles, doing experiments, sometimes just noticing surprising phenomena and then trying to explain them. There's really cool work by, for example, people like Laura Schultz, who's one of my colleagues at MIT, or Lisa Feigenson at Johns Hopkins, looking at how kids just kind of spontaneous play is a kind of informal experimentation, testing out these intuitive theories and trying to resolve anomalies and improve their knowledge, much like the way an early scientist might have worked. So here's a really nice example from a paper from Stahl and Feigenson. That's this figure here that was recently appeared in Science a couple of months ago, where it builds nicely on some of the stuff in the previous slides. This stuff here, where basically they took 11-month-olds, so kids who are towards the end of this timeline where they've kind of started to understand about solidity and support, and then they showed them something surprising. And again, this is just representative of a whole lot of other experiments. I'm just going to show you one, where they showed this baby, the baby's kind of sitting at a high chair. This is the high chair top. They showed the baby a car where the car rolled across a table and then either did the expected thing, like it just fell off the edge, or it did the unexpected thing, it just kept going off the edge. Sort of a cheap trick, easy to fool babies. But looks like it, you know, just keeps continuing off into thin air. Or here, they were violating the solidity idea, right? So the car rolls down a ramp and there's a wall, and either the expected thing happens, namely the car hits the ramp and bounces off, or the unexpected thing happens is it goes through the ramp, or sorry, through the wall to the other side. Okay. Then the key thing is they give the toy, the car to the baby, and they see what happens. And they found two things. One is that, like a lot of other previous studies, when an unexpected thing happened, the kid played more with the toy, as if they were trying to, they were curious. They wanted to see, well, what's going on with this? I'm going to play with this and find out. That's the sort of thing that Laura Schultz and other studies that I'm showing here had showed extensively before. But the new thing was that not only did they play with the toy more when they saw something surprising, but they played with it in kind of the most natural, useful way to figure out exactly what was going on. So when what they saw was a violation of, or something unexpected under gravity, they tried experimenting with the toy kind of by dropping it and seeing if it would fall, right, on their high chair. And here what they saw, though, was a violation of solidity. They played in a different way. They took the toy and tried like knocking it against the table to see if it would go through the table. This one's particularly interesting, right, because it's a very different kind of thing to do. This was an object that went through the wall, you know, kind of this way, and the kid is taking this thing and trying to see, oh, can I make it go through the high chair? That's weird, right? So this is just a simple example of playing that's doing a kind of experiment to try to see what was the source of the anomaly. Is there something funny about this car? Was it just something funny about the wall? What was it? Does that make sense? Okay. So that kind of, that's what real learning is like, in a sense. Okay. One last thing, just to kind of, and then I'll get into the actual technical models but just to sort of tie things back, it's not only about physics, but intentional action. And again, I think this is certainly going to be important for later developing AIs. You see this in language. Our common sense is about minds, not just physics. But these also interleave, and you can see these in these great movies. This one's pretty famous. How many people have seen the Hyder and Simmel movie? Okay, how many people have seen this one here? Okay, was that from a talk I gave, or you've seen it separately? Okay, the one I gave at CVPR. Okay, cool. I'll show the one on the left. It's a little simpler, and this is actually from an experiment with infants around the same age, 13 months, by Southgate and Chibra. And let's see this here. So you could parse this as just objects in motion, a blue ball and a red ball rolling on a green plane, or you could see it as something more like an intentional action. So just watch it again and see how would you describe what's going on if you wanted to tell a story about these characters. Chasing, yeah. Who's chasing who? Yeah. And what is the red ball doing? Running away, yeah. Now here's another question. Who's smarter, the blue ball or the red ball? How many people say the red ball? Yeah, now why is that? How can we tell?
Find like a smaller slit through it,
Yeah.
it can go, but the blue cannot go through it.
Right. That's definitely smarter, the red ball, but the blue ball also looks a little bit stupid, doesn't he? Yeah, the blue ball seems to have what we call a false belief, right? He doesn't realize that he can't fit through those holes. And even more, he has a persistent false belief, right? He keeps making the same mistake over and over again, right? He keeps trying to go through those holes and failing. And that's a sense in which I think we have a kind of intuitive theory of learning, in a sense, right? If somebody fails to learn from making the same mistake over and over again, we think that they're not as smart as they could be, right? It's part of being smart. I mean, that's an intuitive concept. Part of being smart is basically, having good strategies and planning actions effectively, but also learning from your mistakes, right? Be smart, don't make the same mistake over and over again. Now, we don't have evidence that 13-month-olds look at this and judge the characters in quite that way, but what we do have evidence using the same kind of methods is that they understand the chasing and fleeing. And so they understand the goals that these guys have, even though the actual motion is not strongly diagnostic of it, at least in a traditional computer vision sense, right? If you actually look at the motion vectors involved, the blue guy is very rarely heading directly towards the red guy. What he's doing is he's more like taking an efficient path, something like the shortest path in the space, subject to a combination of true beliefs and false beliefs. The true belief is he kind of knows where the red guy is, and he knows where the walls are, but he has this false belief that he can fit through these holes that he can't. And it's that parse of his goals combined with his beliefs, combined with the physics of the situation. You have to understand efficient action, you have to understand and grasp in some form that those agents grasp the constraints of their physical environment. A way you can show that even infants do some version of that is you take away the walls. So just imagine, I don't have this video, but you can find it online actually. Just imagine the same ball motion with no walls there. It doesn't look like chasing anymore to us or to infants. It does look animate. It looks like a kind of playing, like they're sort of dancing with each other. They're clearly not just rolling as inanimate objects, but you don't get the strong sense of this goal-directedness because that's really about this interesting kind of efficient action. I'll skip the Hyder and Simmel, but this is a similar kind of very simple video of just shapes in motion that you can watch on YouTube if you like. And it's amazing how much kind of common sense goes into understanding just these shapes. But the things I want to focus on really are the sort of intuitive physics that's present even in these scenes and the intuitive psychology of goals and beliefs that builds on that intuitive physics. So that's a long introduction to what we're trying to do. And in some sense, I'd be happy if I just stopped there because what I want to convey to an AI audience is we should try to understand this. We're making in our group a little progress on this, but these are really hard problems and most of the cool work is in the future. But I'll tell you a little bit more technically now about how we've been trying to tackle this using ideas of probabilistic programs. So again, I think I asked something like this before, but how many people know what probabilistic programming is? Okay, how many people have never heard of that? Okay, well, cool. It's one of the more cool recent developments in AI. There have been a couple of workshops on this topic. I think there's a special issue of AI Magazine potentially in the works on it. There's a DARPA program called PAML, Probabilistic Programming for Advancing Machine Learning. Anyone heard of that? Luckily, you don't have to worry about DARPA here for the most part, right? Lucky you. But it's something which is, I think, going to be increasingly important in AI, certainly if we want to be able to tackle these kinds of things. The particular kind of, and if you want to learn a little bit more about the approach that we've developed, go to this probmods.org website. I'll show you a few excerpts up from it in a second. The particular approach that we've developed, people mean many different things by probabilistic programming, but I'll try to introduce generally what we're talking about and the sort of general version of the idea. Think of it as an extension or development of graphical models. In particular, we're interested in directed graphical models, like Bayes nets, ones that are naturally capture causal processes in the world. If you know about, say, for example, Pedro Domingos's work on Markov logic and his group, that's a similar kind of idea, but it's built on undirected models, and it's also not as abstract as what we're talking. Well, anyway, it's different in certain ways, but it's kind of similar in some ways. So again, I assume everybody here is familiar with pictures like these, Bayesian networks. Why were these kinds of graphical models so important not only in AI but in many other fields? Because they gave two things: general purpose tools for knowledge representation, for capturing causal knowledge in particular, like the knowledge of a doctor of how diseases cause symptoms. And then general purpose tools for doing inference, so to understand how you could work backwards from a few effects of a causal process, like observing a few symptoms, to figure out, make good guesses about what diseases a patient is likely to have, and then make predictions. Well, if that's the disease I have, then maybe this other test should come out this way, to do kind of diagnostic experiments, like the baby was doing with those toys, to say, well, if there could be two possible diseases that could explain this, let me think of some test I could do that would tell apart from them. That kind of planning of gathering new knowledge, those are some of the many very general inferences that algorithms for Bayes nets supported. But to capture the kind of common sense knowledge I've been talking about with young infants, I think you need tools like this, but they need to have a richer representation of the world, to go back to that theme. In brief, they need to represent the world using richer tools of programs and not just graphs, right? So throughout science, whether it's classic early science like Newton or Mendel or a lot of more modern science, the idea that you capture the causal mechanisms in the world with something like a program that can be evaluated by running it to see what happens, that is very standard. It's probably the dominant way of understanding causal mechanisms in the world. Now, you might not have thought of, say, Newton's laws as a program. You might have thought of them as a set of equations, right? And for simple cases, like, say, two bodies orbiting around each other or a planet going around the sun, you can solve the equations of motion in closed form to figure out that the orbit of the planet is an ellipse. But as soon as you get even three bodies, right, we know you can't just easily solve those equations. You have to basically write a computer program, set up some differential equations and solve them, and the solutions could have all sorts of complexity when you have an n-body system. And that is just the nature of science. In the case of genetics, say, you could think of Mendelian genetics as a kind of probabilistic program, right? It's a structured stochastic process. There's some random events that happen on interesting hidden variables of genes, and it gives rise to certain patterns of observable events in the phenotypes of pea pods or whatever. And in the very simplest cases that Mendel talked about, you could do the math analytically and derive the results and try to look at patterns of pea pods over a couple of generations and fit the parameters of the theory. But in any, complex case, you can't do the math analytically, and so people do a whole lot of simulations, Monte Carlo simulations and other sorts, in genetics. And the same thing comes up, whether you're doing, modeling galaxies colliding or the climate or rivers forming and so on. This idea that we formulate our scientific theories as something like programs, where the program structure captures the causal processes, and then we put probabilities on the parts of the program we don't know, whether it's parameters or hidden variables, other sorts of inputs. I think this should be a very familiar idea. So that's what we are trying to do here, basically. These are just a few examples of web pages from this tutorial, the thing, this probmods.org, it's this web book, which is a very lightweight, simple introduction to probabilistic programs and using them to model cognition. It was written so that even high school students could understand. But what's cool about it is that it has all these examples that are in these runnable code boxes. So these are examples of this church probabilistic programming language, which is built on top of Scheme. Some people, of course, really like Scheme. Some people really hate it or just groan about it. And at this point, there are many similar kinds of languages built on whatever your favorite traditional programming language platform. The key thing, what's nice about the pure functional nature of scheme, relatively speaking, is it shows the analogy to Bayes nets very clearly, right? You basically, a probabilistic program is a bunch of stochastic function definitions which call each other, just like variables in a Bayes net, where you have the parent relationship in a Bayes net that specifies the direct or irreducible causal dependencies of each random variable. That's basically what you have in a probabilistic program. The key is that it's a description of the forward or the causal model. And then you have query programs, like this thing here called rejection query or MH query. So a lot of it is with some kind of Monte Carlo, but not only these days there's variational queries and other sorts of things, but they're basically like an inference engine where you take a program that describes the causal direction and can run it backwards to do basically arbitrary conditional inferences. Now, the particular way we're using probabilistic programs, and here I'm going to try to bring this back now to the kind of the core knowledge of infants, is what just kind of informally I like to call the game engine in your head. So probably many people are familiar with game engines, but just curious, how many people know what a game engine is? Okay, basically everyone in this crowd. Anybody, how many people have written a game in a game engine? How many people have written a game engine? Okay, so that's telling, right? But basically, how many people have written a game not in a game engine? Okay, a lot. But these days, particularly if you're going to write, how many people have written a first-person interactive, either shooting or exploring a 3D world type game, not using a game engine? Okay. How many people younger than 40? Okay, no, sorry. I'm older than 40, I'm allowed to say that. Okay, right. So the point of game engines is they provide useful general tools for game designers so that they don't have to write everything from scratch if they want to build a really cool immersive experience, right? They have a graphics engine, they have a physics engine, usually of some form. They usually often will have some kind of planning engine, very simple kind of game AI to handle the non-player characters, right? Like if you want to have a base, some guards at a base and the player is trying to invade the base or something and you want to make it challenging, you'll have some guards with some guns maybe, and you'll give them simple goals and simple planning capacities where they might say, well, if you see the player in your line of sight, they'll model like the line of sight axis. If you see the player in some cone of vision, then shoot at them, or if they're really far away, go towards them until you're close enough and then shoot at them, right? So what I want to put out there, and it's sort of a conjecture, hypothesis, I'm sure it's wrong, but it's maybe a little bit right, it's useful, is that these kinds of tools, in particular graphics engines, physics engines, and these very simple kinds of AI planning engines, that we put into modern game engines that allow somebody to make a whole virtual world and sort of think about the story of the game and the drama of the game without all the technical details of programming it. That something analogous to that is in your head, that the stuff that is built through some combination of genes and experience over, say, that first year is this stuff, right? And in particular, this stuff in some form wrapped inside a probabilistic inference framework. So the reason why we want to think about probabilistic programs for this core knowledge representation is that it's not enough to just play the game forward. You have to be able to reason about it. You have to be able to, say, observe the output of the graphics engine and reason backwards to the 3D world that gave rise to it. So this is a kind of an old idea. Vision is inverse graphics. And if you saw at CVPR, I gave a few talks at CVPR, so I'm not sure which one you saw, or whether you might have seen some of the work. We have a great student in our group named Tejas Kulkarni who gave a talk in the main conference about basically probabilistic programs which take graphics programs and run them backwards to do interesting vision problems. I won't talk about that here. And I say I only have about 10 minutes. So what I'll mostly do is talk about the physics engine part of things and maybe a little bit about the planning engine. But the basic idea is to say, define these world models, which, you could look at this and you could say, well, those look like directed graphs. Why is this different from Bayes nets? And in some sense, that might be right. This is, if you know the directed graph formulation of a hidden Markov model, the picture I'm showing down here kind of looks like that, right? But the key is that if you were to represent this as a traditional Bayes net or graphical model, you'd have nodes and arrows that are kind of infinitely thick. Like the world state isn't just a fixed finite dimensional random variable, but it's something like a whole CAD description of a scene. I mean, we don't really know how to describe this yet, but it's a description of a whole bunch of physical objects in a three-dimensional representation with their physical properties like masses and stiffnesses and so on and friction. And then this arrow isn't just a transition matrix in an HMM, but rather it's a physics simulator, right? So we think that if you really want to capture intuitive physics, vision, intuitive psychology, you need these thick arrows that we really can only capture with programs. The same way in many other areas of science, that's the way we capture our knowledge. Now, I'm not going to say anything really in this talk about the way that we do inference. I'll just say if you want to understand what are these, if you like, inference programs that run on these probabilistic programs, you can read about them in various places, such as probmods.org, or Noah has another book which is linked off of that web book called DIPL, which is Design and Implementation of Probabilistic Programming Languages, which describes how to actually implement some of these learning algorithms. Inference algorithms. The only thing I want to say about the inference algorithms is that the first ones that were used in this church language, and as well as a lot of other probabilistic programming languages, often seem kind of slow by conventional machine learning standards. Maybe, I don't know, some people here might be troubled by that, other people probably wouldn't be. But the key is that this is an area of active research and progress. This is a lot of the focus of this DARPA program that I mentioned, the one called PAML, is really trying to develop better, faster, more general fast inference algorithms, some of which for certain kinds of probabilistic programs, like those involved in vision where you're inverting a graphics engine, can be actually quite fast. I'm not going to talk about that here. I'm just going to show you in a few minutes how we're using these to capture intuitive physics and intuitive psychology. So here's an example of a task that we studied. That's, you could, from an AI point of view, you might call this a blocks world task. I'm one of the people who thinks that blocks world was a really good idea, and that computer vision and AI, if only you study it in the right way, you can make a lot of progress by studying perception, reasoning, action planning, language in simple kinds of displays like this. So this is an example of an experiment or stimuli from an experiment we did. This is work that Battaglia did, who's now at DeepMind, which I guess is sort of one of your competitions in some sense, right? Like, if I think of really cool, exciting places where lots of smart people, mostly young folks, have come together to work on big AI problems, they represent another one. I was just there last week, and I don't know, it's a fun place. I think it shows something of the good vision of DeepMind, that they're not just doing deep learning, but they're hiring people who do this kind of thing too. So here's an example of the experiments that Pete did with Jess Hamrick and me. We showed people these stacks of blocks, kind of inspired by the game Jenga. How many people know the game Jenga? Yeah, that's always, people know Jenga better than almost anything. Good. So it's a fun game. It really taps into your intuitive physics. And the way we tap into it here is we show these stacks of Jenga blocks, basically, and we ask people to judge how likely they are to fall over. So how stable is any one of these scenes under the basic physics we know, gravity, friction, and so on. And hopefully you all agree that some of these scenes, like the ones in the upper left, are pretty stable, they're fine, whereas these ones here look like they could fall over any moment. And we can tap those intuitions in various ways. Experimentally, we can ask people to just rate on a scale of 1 to 7 or do other things. You'll get the same answer pretty much no matter how you do it. And then we can build models using these probabilistic programs. So I'll just illustrate the basic idea of how this model works, but if you want to learn more about it, you can check out this recent paper we had in PNAS. And also the Tejas Kulkarni CVPR paper, which in a sense is mostly focused on this part, how we go from an image and sort of kind of run graphics in reverse, in a sense, to make a guess at the configuration of blocks in the world. This is like a 3D CAD type model that gives rise to an image like this. There's a very simple version of that in this PNAS paper. And then you say, okay, now I have a guess of the world state. Let me make a prediction of stability by running this forward in a physics game engine. So in particular, we're using, I think it's a kind of a ODE-based engine, the Open Dynamics engine. You can use many different kinds of things here. A key is that the graphics programs we use and the physics programs we use are really meant to be the simplest, fastest ones you could get. It's not like, we're not trying to do inverse Pixar here, but it's more like inverse game engines, right? Things that just look good enough that you can run as fast as possible, because that's really the setting of common sense reasoning as opposed to Hollywood movie making. So we just take a very simple kind of approximate physics engine, run a few time steps forward, and get something like that, right? So this is, in a sense, one guess of what will happen after a few time steps is the blocks will mostly fall over. Now here's another guess, which involves both a slightly different guess at the scene, the 3D scene of the objects, as well as how they fall. And who can say, is that really what's going to happen? Is that really what's going to happen? I mean, nobody can look at this and tell you, right? And for our purposes of common sense reasoning, it doesn't matter. Any one of these simulations is good enough to say, yeah, I think most of the blocks are going to fall over. So that's the basic idea behind our models here. And this, I'm just illustrating how we test these in experiments. So what I'm showing in this graph here is I'm plotting the average judgments of humans versus the sort of average predictions of this model, which just runs one or a few of these few time-step simulations. And each dot, each cross, is one of these configurations of blocks. The error bars, those hashes show error bars. Going up on the vertical axis means people think it's much more likely to fall over all of the blocks. Down here means it's stable, according to people. And you can see people will make graded judgments, filling out this whole spectrum. And then similarly along this axis here, the more you go out in this direction, the more the model is saying, yeah, I think that's really going to fall. And the basic thing I want you to get from the graph is just that this model does pretty well. It's a very simple model in a certain sense. It's simple in that we just took a physics engine and did a little bit of probabilistic inference on top of it. We just allowed for one of two possible sources of uncertainty. You might not know exactly where the blocks are, so you can't perfectly localize objects in 3 dimensions from a 2D image. But also, you might be a little uncertain about the forces in play. So you know about gravity and friction, but maybe there could be every so often, some other perturbation, like somebody could bump the table or the wind could blow. And we have reasons to think that our intuitive physics is robust with respect to at least these two kinds of uncertainty. Yes, good. And the main thing I want to point here is that if you don't have those sources of uncertainty, but you just use the noiseless ground truth physics, it doesn't do nearly as well. In fact, it actually has some illusions, like some things like this one here, which are actually physically stable, but look to us unstable because of the ways that probability is wrapped into our minds. To make a similar point on the intuitive psychology side, so here again, now the programs are these simple kind of like very simple game AI level planning programs. Or you could say that it's AI as instantiated in, say, GPS navigation systems, right? Except for the GPS part. But like you have sort of very simple shortest path planning algorithms and an agent who forms beliefs about the world based on their line of sight, what they can see. And then we can say our model is basically that people's common sense or the original intuitive psychology is applying that kind of model to agents we see. So observing their actions, like the actions of balls rolling around, and working backwards to say, well, what do I think their goals were, or what beliefs do I think they had, maybe based on some combination of what I see in the world and where they are. And we can similarly build very quantitatively predictive models of human action understanding in scenes like the ones I showed you with the red and blue balls. So here's an example of a scene where you're watching kind of an overhead scene. This agent's moving in some room. There's one of 3 possible goal objects. There might be some walls in the way. Maybe the wall has a hole in it that the agent could go through. Since I have very little time, I won't tell you the details other than just like with the stimuli with the blocks, we do a lot of manipulations. We vary the geometry of the room, where the objects are, what path the agent takes. We query people at different points along the path to see how your understanding of the action evolves as you get more and more evidence. And we then measure data like this. So these plots here are examples of judgments of people are making about the agent's goal over time in different environments. And you see they move up and down a lot in ways that are sensitive to the structure of sort of effectively efficient planning. Like the model is assuming, if you're familiar with inverse reinforcement learning or inverse optimal control, it's a similar kind of idea. You're assuming that the agent is trying to maximize their expected utility, where they get a big reward for getting to their goal and there's a small cost of each action. And then basically by interpreting these different patterns of motion and saying what's the most likely goal, you can do a really remarkably good job of predicting people's judgments about the agent's goal, right? So you can extend this to a setting of belief also. So here's an example where, maybe this is just the last example I'll explain. But here's an example where you see an agent moving. Well, let me just give you the story and you see what inferences you make. Okay. So this is like, I don't know if they have this around here, but a lot of universities, right, have these food carts where you might go for lunch. And so on this little university here, there's 2 parking spaces where a food truck can park on any day. There happen to be several different food carts that patrol this university. So there's a Korean truck that happened to park here today. There's a Lebanese truck that parks in this spot. There's also a Mexican truck, but it didn't make it today. On some days, there might be a Mexican truck in one of these spaces, or maybe a space could be empty. Now, imagine we have our hungry grad student here who comes out of his office, and this is a building, so he can only see, he can only form beliefs based on his line of sight. So he comes out here, he can see what's on this side of the building, that there's a Korean truck there. He can't see what's on the other side. So what does he do? Well, he goes here, he walks past the Korean truck to the other side, where now he can see what's on the other side. And at this point, he turns around and goes back to the Korean truck. So the question for you is, what's his favorite truck? Is it Korean, Lebanese, or Mexican? Mexican, yeah. So that's pretty cool. And what's his second favorite truck? Korean, yeah. So it's kind of neat that what you see here is very clearly that his favorite truck is not one that's even present in the scene. You have to understand what he is maybe expecting to see or hoping to see. And that together with the particular way that he moves in this scenario tells you not only what he likes, but also maybe what he thought originally. So we can also ask people, when he came out here and started moving this way, what did he think was on the other side of the building? And people, as well as this model, think it's most likely that he thought the Mexican truck was there. It's a kind of inferential optimism. But it sort of makes sense, right? If he didn't think the Mexican truck was likely to be there, for example, if he thought the Lebanese truck was there, then he wouldn't have even done that, because the Lebanese is his least favorite truck. So if he was confident that the Lebanese truck was there, he just would have gone straight to the Korean truck in this scene, right? Okay, so this is just an example of the kind of joint inference about people's beliefs and desires that we think people can make very quickly and readily, and just by watching people move around in a scene like this. And across these and a bunch of other experiments like the one I'm showing you here, this simple kind of inverse planning model planning under uncertainty is able to capture quantitatively what people can do. All right, I guess I was a little optimistic about what I could fit into this talk, because I do have a bunch more slides, but I will skip through them. I guess I got kind of carried away talking about the developmental psychology, but hopefully that's interesting to you. If you want to look more about, like, for example, the ways in which these kinds of models can really underlie common sense reasoning, and not just any one task that I showed you, you can, is that me saying time to end up the talk? You can look, these are all examples of inferences that are just in that original PNAS paper, the Battaglia et al. One on intuitive physics, where we give people a whole bunch of judgments, including kind of weird judgments like this one, where to show that it's not just, you're not just making judgments that are the same things that you've always, that you've got a lot of training experience in your life. You might say judgments of whether things are going to fall over or not is something that you could have learned in some direct way from experience. But we ask people questions like, in this one here, if the table is bumped hard enough to knock some of the blocks onto the floor, is it more likely to be red or yellow blocks? And if you look at all these examples, like, how about here? Is it red or yellow? Red. Yeah. How about here? 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 Yeah, you get the idea. Here? Here? Yeah, you can just keep going forever. And we don't think there's any way to address this other than by running some kind of simulation, which, again, yeah. Oh, just done. OK. Well, anyway, so, yeah. So you can read this paper to get a lot of examples, and then you can study other things in physics. And we can talk about learning maybe over lunch or later on. But I think just to frame the problem, right? The problem is, how can we build a system that can solve all these problems that in some sense, again, through some combination of what you set up from a genetic program or an AI we call hardwiring plus experience can learn to build this kind of a sort of a physical engine reasoning system, or the inverse planning one. It's basically, it's a problem that we're starting to work on. It's a really hard problem, but I think it's one that, with the right kind of mix of science and engineering, we might make some progress on. I'll just skip to my conclusion slide. Europe, which is there. Okay, it was down here. Okay, so I've tried to argue that we should, to complement really the approaches that that a lot of work in AI is focusing on these days, based on language or language-like knowledge representation reasoning. We should also look at this more pre-linguistic kind of core knowledge representation reasoning that you can see even in young children that we think is really centered on an understanding, an intuitive understanding of physical objects and agents that we think we can start to capture with a certain kind of probabilistic program, right? That really is generalizing what we are used to valuing from, say, Bayes nets, the idea of causal models and general algorithms for doing inference on them, but extends to the richer representations that can actually make the world real, the kind of things you see in a graphics engine or physics engine or a simple planning engine. And I think, again, understanding how to do learning with these and how to build language on top of them is hard, but those are challenges that we really need to work on, and we'd love to talk more with you guys about that. Okay, thanks.